In this video, I'm going to show you how to simplify and combine radical expressions. So, let's take a look at what we have here. Nth root of BC equals the nth root of B times the nth root of C. So all of this is telling us is that if we can split up one radical into two radicals. But we can do vice versa as well. If we have two radicals, we can multiply them together as long as they have the same index. And what do I mean about index? I'm talking about the number that represents this n here. So if they are the same, you can multiply two radicals together to become one radical with that same index. So let's get started. Let's multiply radicals. For example, A. We have 2 times the square root of 3 times 3 times the square root of 5, or for short you could say 2 radical 3 times 3 radical 5. Now the 2's on the outside can be, and the 2 and the 3 on the outside can be multiplied together. So let me write it out. You don't have to write it out. You could just simply multiply this together. But I'm going to put the same index radicals together and the numbers together. So I'm just saying you can multiply the regular numbers together, 6, and you can multiply the radicals together because they have the same index. Both of these are square root. Alright, next for B, we have the same square root symbol here. So if you don't have anything present in that little V part there that you know that they are considered to be square roots, and you can multiply what's under the radical together. 3 times 12 is 36. Now here's a different case where you can actually simplify this because 36 is a perfect square, correct? 36 is a perfect square. So the square root of 36 equals 6. So always simplify when you have radicals. If there are perfect squares under that radical, you must simplify. Or if you have perfect square factors under that radical, you must also simplify. Let's move on to C. Here you have 2 times the cube root of 6 times 5 times the cube root of 4. Again, you can multiply the 2 and 5 together, which gives you 10, and then you can multiply the cube roots together because they have the same index. Keep that same index though, so the cube root of 24. Now, don't just think you're done. Always look under that radical to determine whether you have, in this case, a perfect cube, because you're dealing with a cube root. You need to ensure that you don't have a perfect cube factor under that radical, and you do because 8 is a perfect cube. So by now you should know that it's best to be familiar with your first 10 perfect squares and about your first 5 perfect cubes. Now you can split up the radical into 2 radicals at this point if you would like. And then you will see that cube root of 8 is equivalent to 2. So that's 10 times 2 now times the cube root of 3. So your final answer is 20 times the cube root of 3. Similar to the product property of radicals, you can also use the quotient property of radicals, where you have one fraction, you have a radical with one fraction, or one radical and a fraction under it, and then you can split it up as 2 radicals, right? So again, it works the same way with division as it worked with multiplication. So let me show you what we mean. So if you have the square root of 36 over 9, one way of possibly simplifying this is splitting up the radical into 2 radicals like so, and then simplify each separately. The square root of 36 is 6, the square root of 9 is 3, and then 6 divided by 3 is 2. Now, a completely different way of doing this one, and it was possible to just divide 9 into 36, which is 4, and then you also can simplify it to 2. So these are the same answers, just showing you that there are two different ways you could have approached that particular problem. Let's move on to B. Similarly, you have the cube root, but you can split it up as the cube root of -8 over the cube root of 64, and then simplify each radical separately. You'll get cube root of -8 is -2, and the cube root of 64 is 4, because 4 times 4 times 4 is 64. Now, -2 over 4 simplifies to -1/2. Moving on to C, let's split this up because you can't do anything but split it up at this point, and you'll see that your final answer is 2/5. Let's move on to D. You have the square root of 28 over 9, so square root of 28 over the square root of 9. Again, we need to look at the numbers under the radical to determine if they are perfect squares first. And you probably notice that this 9 is on our perfect square list, but 28 is not. However, 28 contains a perfect square factor of 4. So we need to split up 28 into 4 times 7. Of course, the square root of 9 is 3. But we need to simplify the square root of 4. Now, you could split it up, write it out like so, or you could have just simply wrote 2 square root of 7 over 3, because the square root of 4 is 2. Let's move on to E. We have the cube root of 24 over the cube root of 27. Now, 27 is on our perfect cubes list, so that's not an issue. But 24 is not. However, 8 is a factor of 24, so you can split it up as 8 times 3. And of course, cube root of 27 is 3. Now, what is the cube root of 8? Cube root of 8, I'm not going to write it out this time. I'm just going to simply write down that the cube root of 8 is 2. But don't forget to put your little cube root symbol here, 3 over 3, for the remaining part of the solution. And F is a little different, right? Because we have variables involved. And but I'm gonna show you one approach you can use. Since these are already split up, you could actually do better by putting it as 1. So 4x squared y over xy. That will allow you to eliminate, for example, the y's, and that will allow you to eliminate one of these x's. And because of that, we wrote it as one radical. Then we could rewrite this as the square root of 4x. Now, again, 4 is a perfect square. So if you want to split it up like so that you can see that the square root of 4 is 2, but we couldn't do anything with the square root of x, so it remains under, that x remains under the radical. Now, in order to add or subtract radicals, the radical must have the same index. And as you can see in red here, that's the index. And it must also have the same radicand. And the radicand is what's under the radical. So, for example, in this first example here, 5 radical 3 minus 4 radical 3 plus 6 radical 3. Notice that all three of these have the same index and radicand. Therefore, we can combine this. Now, you don't have to necessarily write this out as, but I'm just showing you that we can combine this 5 minus 4 plus 6, sort of acting like terms. So what we're doing in our head is 5 minus 4 plus 6 radical 3. You don't have to write that out. As long as you realize that it ends up being 7 radical 3, you could really just go from here to here. But I wanted to show you where the 7 is coming from. 5 minus 4 is 1, and 1 plus 6 is 7. So let's go to the next problem. Notice that we do not have the same radicand, even though we have the same index. So what do you think we should do at this point? Well, we're going to have to simplify each radical separately. For example, this 8 is 4 times 2, and this 18 is 9 times 2. So again, I'm not going to write it out, split it out. Well, let me write the first one out. So this is 3 times the square root of 4 times the square root of 2. So it's a lot of writing when you write it all out, but if this helps you, please write this out and split the radicals up every time. Notice that the square root of 4, we can simplify that, and the square root of 9, we can simplify that. So really what we have is 3 times 2 radical 2 plus 5 times 3 radical 2. So that's 6 radical 2 plus 15 radical 2. And because we have the same radicand and index, we can combine these two, and it becomes, we add the 6 plus the 15, which is 21 radical 2. So that's our final answer. Let's move on to 3 radical 12. So that's 3 times what perfect square factor is in 12? That's 4. What about 5 radical 27? What perfect square factor is in that? 9. So here again, we have the square root of 4, we have the square root of 9. So 3 times 2. So I'm not going to split it up. I'm just going to go right to it. Square root of 4 is 2. That 3 remains under the radical. And then the square root of 9 is 3. The other 3 remains on the radical. So 6 square root of 3 minus 15 square root of 3. That is negative 9 square root of 3. Let's move on to C. To the right here, we have 4 and 8. We've split that up with 4. That's 4 times 2. And of course, 10 times square root of 2. Square root of 2 is already simplified, but over here, notice that the square root of 4 itself is 2. So we're going to simply put 2. There's no radical left remaining on that part. So we have 4 square root of 4 is 2, and then we have a 2 still remaining under the radical. And then at the end here, we have a 6, simply a 6, because 3 times 2 is 6. Then we have 8 times the square root of 2 minus 10 times the square root of 2 plus 6, which is negative 2 square root of 2 plus 6. Now, another way you could have written this answer was 6 minus 2 square root of 2, just in case you wrote it the other way. Okay. Moving on to D, we have 5 times the cube root of 81. Then this is when you look at your perfect cubes list, not your perfect squares list. And you will notice that 27 divides into 81. That's 27 times 3. And then with 24, 8 divides into 24. So here we go. Cube root of 27 is 3. It goes outside of the radical, but that other 3 remains on the inside. Cube root of 8 is 2. It goes on the outside of the radical. So we have 15 times the square root of 3 plus 6 times the square root of 3, which equals 21 times the, I've been saying square root of 3, but it's the cube root of. All right, here we have some examples. You should try these and put your final answer on the right. So pause the video, try it out, and see what happens. So hopefully you've tried out the problem by now. If not, pause and then play. But I'm going to proceed. We have 3 times square root of 20. What perfect square goes into that? 4, of course. And then we also have 45, and we know 9 divides into 45. So here we have 3 times the square root of 4, which is 2. Times the square root of 5 minus the square root of 5 minus 2 times 3 because of that square root of 9. So what we have is 6 square root of 5 minus a square root of 5 minus 6 square root of 5. So notice what you could have done is cancel out these 6 square root of 5s, and it's going to leave you with this negative square root of 5. Or you could have looked at it as 6, right? You could have looked at it as, if you wrote it out, that's 6 minus 1 minus 6 square root of 5. And if you did that, you'll notice that you still end up with negative 1 square root of 5, which is the same as negative square root of 5. So if you put a 1 here, it does mean the same thing. However, it's conventional that we do not write 1s as coefficients or powers. Let's move on to number 2. We're switching it up to the cube roots. So we got to think about perfect cubes. Now, 5 times the cube root of 2 is already simplified. However, 16 contains the perfect cube 8. And what about 54? 54 contains 27 as a factor. So we're going to write it out like that. Now, the cube root of 8 equals 2. And the cube root of 27 equals 3. So what we have is 5 times the cube root of 2 minus 4 times the cube root of 2 minus 18 times the cube root of 2. And what do you have? 5 minus 4 is 1, and 1 minus 18 is negative 17 times the cube root of 2. So hopefully you have negative 17 times the cube root of 2. Now recall that you've simplified radicals with variables under it. And let's do a brief refresher on what we do when radicals are under the denominator, when radicals are under the radical. So of course we know how to handle that 8. That's simply 4 times 2. But since we have a cube here and it's considered to be 2 here, then we're going to break the x up into as many x squares as possible. So it'll be x squared times x. And then you'll leave a little room in the front of your radical and go down the line. The square root of 4 is 2. So that goes on the outside. That goes on the outside. This 2 stays on the inside. And then this square root of x squared goes on the outside, but the other x remains under. So this is how we simplify radicals when variables are under the radical. So let's try a few more. We have 3 times 12, radical 12x cubed, so that's 4 times 3. But again, that's x squared times x minus 2x times the square root of 3x. Now the square root of 4 is 2, so it goes on the outside. That 3 remains under. Again, square root of x squared, that's x. That goes on the outside. And then we have an x under there. So what we have is a 6x square root of 3x minus 2x square root of 3x, which equals 4x times the square root of 3x. Moving on, for B, we have 10. All right, so we have 10 times the cube root of 8. Now, notice that that is a perfect cube. So we're going to come back for that. 8 is a perfect cube. But let's split up this a to the 4th, because we're going to break up the a's into as many a cubes as possible. And this is why we're going to break it up, because we have a cube root symbol, and we know the cube root of a cubed. So we're going to split up the a's into a cubed times a, because a cubed times a is a to the 4th. And we don't have enough b's to split it up, so we're going to move forward. So 11a times the cube root 27 is also a perfect cube. So let's wait till the next line to start taking numbers out. We have 10 times cube root of 8 is 2. So we're gonna take that cube. We're gonna take that perfect cube root of 8 which is 2. We're going to take that 2 out. And then we have cube root of a cubed, which is a, so a goes out. However, these remain under ab squared. Similarly, cube root of 27 is 3, so we're going to take that out and leave ab squared under. So what we have is 28 cube root of ab squared plus 33a cube root of ab squared, which is, when you put these together, because they have the same radicals there, you have 53a cube root of ab squared. Let's move on to C here. These do not have variables, but I added it because it was a fraction, and sometimes if you don't see a fraction, you'll think that it's not possible to for you to do those ones without me showing you first. So let's proceed. 96. Now there's a perfect square of 96. 16 is a perfect square that's a factor of 96. So we're going to write it like that. And also 9 is a perfect square that perfect square factor of 54. Now the square root of 16 is 4, so we're going to take that 4 out and leave that 6 under the radical. And the square root of 9 is 3, goes outside, and then we have another square root of 6. Now we need to figure out how to multiply 3 over 8 times 4. So we're multiplying fractions. Now what I probably would do is cross cancel, because I know that this 4 is over 1. 4 divides into 8 2 times. So I know this is 3/2 radical 6 minus, and I know the 3's will cancel over here. So you have 2 times the square root of 6. Now, since we have the same index in radicand, I know that we can combine 3/2 minus 2. Now, again, these are fractions, so what you're really doing is figuring out what is 3/2 minus 2. Now, if you want to put that over 1, great. If not, as long as you know how to figure it out without that 1. Then you can multiply top and bottom over here by 2, since the LCD is 2, minus 4 over 2. That's negative 1/2. So your final answer here is negative 1/2 radical 6. This also is the same as writing negative radical 6 over 2. These are the same because this is negative 1 times radical 6, which is negative radical 6. Now, as a review, in order to multiply radicals with other radicals, what needs to be the same? Well, the index has to be the same. But what about the next one? In order to add or subtract radicals with other radicals, what needs to be the same? Actually, the index and the radicand needs to be the same in order to add or subtract. So this concludes the video on simplifying and combining radical expressions.